this and then play it for period 6.
Yeah, you can use my hotspot.
Alright, we'll see. So, here's how we do this. Every change on the pH scale, you multiply the strength by 10. Sound with me? So, what does that mean? If you have a pH of 3, and then it changes to a pH of 4, the pH of 4 is 10 times less acidic or 10 times more basic. If you have a pH of 3, and you increase it to a pH of 6, a pH of 6 would be 10 times 10 times 10, which is 1,000 times more basic, or 1,000 times less acidic. And then the same for the other direction. If you went from 7 to 5, that would be 10 times 10. 5 is 100 times more acidic than 7, or 5 is 100 times less basic than 7. So it depends on how you word it and which way you're going. That's the whole thing. That's it. If you can remember that, you'll be in good shape. However, this is a little bit trickier. So it's saying the H plus changes by a factor of 10. So that's like going from 3 to 4. This is 1 times 10 to the negative 3 moles per liter. And 4 would be 1 times 10 to the negative 4. That's what the question means. This is a factor of 10. It's a power of 10 and whole exponent there. So when the hydronium ion, increase, so we're going this way. This number is bigger by 10 times. So 10 times this number will give you that number on a calculator. That's why we had the calculators out yesterday. So the answer to the question is number 2. And the reason is because this is actually a pH of 4, this is a pH of 3. The difference here is a factor of 10. The difference here is a factor of 10, but it's only 1 unit on the pH scale. The factor of 10 is the concentration, so that's 10 times different. This is just 1, right? 3 and 4 is a difference of 1. So you need to understand that relationship. It's a great review question for what we did yesterday. So I'm just going to repeat myself one more time. Every change on the pH scale is a factor of 10 when you're talking about H pluses or H3O plus. So, very typical Regis question. Again, that's a harder one. Sometimes what they'll do is they'll say, all right, a solution went from a pH of 8 to a pH of 6. By what factor did the H plus concentration change? And then they'll give you 10, 100, 1,000, 10,000. So they'll give you the factors. You need to know, oh, I'm going 1, 2. That's 10 times 10. The answer would be 100. What's up, Will?
I should have my review sheet for you and the other thing you wanted to see from yesterday. Pretty sure.
Oh, yeah.
That's it. Do you just want to keep it?
Nope. Okay. Hold on. All good?
Okay.
All right. Thanks, Will. All right. So, hopefully some of you who were confused, that makes a little more sense. Again, just repeat myself over and over here. This is a factor of 10. Every change is a factor of 10 with respect to the ions. That's really the relationship here. All right. So, take out your notes. Yesterday, I think we left off with a question. I think I answered it. I want to say it was, you had a solution with a pH of, I don't know, someone read it to me here. 6, was it? We started with a 6, ended at an 8?
4 to 6.
4 to 6, okay. So, I'm just going to repeat myself here. You had a solution with a pH of 4, you add a base to it, now your pH ends with a 6. The question wants to know how many times more basic is this solution. So I just went over this. I'm going to do it again to make sure we really get it. This concentration is 1 times 10 to the negative 4. This concentration is 1 times 10 to the negative 6. If I divide this number by that number, I get 100. The answer is 100 times. Why? Because it's 2 decimal places bigger. This is 0.1, 2, 3, and a 1. This is 0.1, 2, 3, 4, 5, and a 1. Yesterday, I think it was actually Jake and Silas were talking about just counting zeros. So you have 1, 2, 3 zeros here, 1, 2, 3, and then you have 1, 2, 3, 4, 5. That's 2 zeros more. That means this number is 100 times stronger. Maybe that doesn't make sense to you, but that's exactly what I'm getting at. This number is 2 decimal places bigger, meaning it's 100 times bigger than this. Meaning, this is 100 times more basic, this is 100 times more acidic. It just depends on how you define it. Questions for me? I keep saying the same things, but that doesn't always mean you get it. Questions? Speak now. Reagan? How we doing? Good, really happy. Nothing, just smile, almost smile. Hey, did you guys win yesterday? How was it?
Yeah, we won.
Oh, nice. Middleburg's good, right?
Yeah.
Alright, well you beat them, good. Alright, so I'm gonna leave that alone. We're gonna learn something new. Do you have reference tables out?
No.
K, L, and M, and we're gonna introduce something new here.
I got cleared yesterday.
Oh, did you play?
Yes.
Oh, nice. Alright, I'm gonna do this up there since I'm not here period 6. I'm just gonna show you more of what I've already shown you a couple times.
You can just hold the tablet back there.
Yeah, I don't feel like moving everything around. I'll just do it up here. It's just easier. Alright, so. Listen, man, you laugh all you want, but I like my eyes. I got acids and bases here. If like one drop of this got my eye, it could ruin my vision. So,
They can see my vision's already messed up.
What?
So they can't see what you're doing.
yeah, no, I'm gonna hold it up.
You want one of us to hold it?
No, I got it. I got it. All right. So, go to the back of the reference tables. Try and guess which equation we're going to learn right now.
Titration.
Titration, yes. In our notes, I want you to write. I'll take these off for a second. I like writing with purple. What do you guys, how do you feel about purple? You like it?
I'm ready with where's the pen?
Really? Huh.
What did you say?
Titration. Here's a brief definition of titration. It's when an acid and a base react, creating a neutralization. I'm actually teaching two things at once. I'm teaching neutralization and titration, so just kind of explaining that up front. It'll make more sense in a few minutes. An acid and a base react, creating a neutralization reaction. And actually, let me do this. Titration, neutralization. That makes me feel better. I do that. Titration, neutralization. An acid and base react, creating a neutralization reaction. The concentration of an unknown acid or base can be determined. And most of that probably doesn't make any sense right now. I realize it. I'm going to show you with the beaker here briefly. Show you a titration setup, which I have over here, which we'll be doing in lab next week. But then I'll explain it. And this all relates to the formula on the back of the reference table. We might as well write that down. On the back, I believe it is MA times VA equals MB times VB. Is that true? Yes?
Yes.
Yes. Now, does it tell you what MA is and VA and MB and VB?
Yes.
What's MA?
Molarity of H plus.
Molarity of H plus, which means acid. That's what the A stands for. What's VA?
Volume of the acid.
Volume of the acid. What's MB?
Molarity of OH.
Molarity of OH minus, which means base, and VB is volume of base. It literally tells you exactly what to plug in here. What's nice about this is on a Regents, it's very clear when you're supposed to use this. It's the only acid-base calculation there is. It's the only one. So we're going to start learning it right now. I have a worksheet I'm going to hand out maybe in about 15 minutes. Because that's what my plan, if I'm not here 6, is they're going to watch this, they're going to start working on the worksheet. I'm going to have you guys do the same thing. So we're going to learn how to use this equation. But first, let me explain what this means, and I'll show you. All right. So, first thing, let me write the reaction, then I'll show you. All right. So a neutralization reaction Now, if I say neutralize, Kara, what do you think? Neutralize. What pops in your head? Anything? It could be completely unrelated chemistry. Neutralize. pH is 7, very good. All right, I like that. Amanda, when I say pH is 7, what do you think of? Water. Yes, water is always formed. Always. Very good. Zeke. If I take hydrochloric acid and NaOH, sodium hydroxide, let's give a little AQ here. AQ. What do you think the two products will be? Water, good. This is a neutralization reaction. We have an acid and a base. And a salt. What kind of salt? Actually salt. NaCl. Very good. Now I'm going to write water HOH. Please write it that way. Just so I can show you the double replacement a little bit easier. So salt is salt and water is water. I know that's profound. This is an acid-base reaction. It's also called a neutralization reaction. Vanessa, why is it called a neutralization reaction? Good! Yes, I was hoping someone would say that. They cancel each other out. What's left? Water. So this has a pH less than 7. It's probably close to 1. This has a pH greater than 7. Let's say it's 14. Well, if you mix a 1 with a 14 and everything is equal, the same amount of both, you should get a pH of 7. That's what neutralization is. So ultimately what's happening here is the H plus from the acid, and I want you to write this, is reacting with the OH from the base, creating water. In your stomach, right now, you have stomach acid. Everybody does. All the time, there's stomach acid. It's like a 0.8 pH, something like that. pH of 0.8. When you eat food, that usually, well, it depends, but you can increase that pH. When you, I'll give you a better example. If you were to drink Pepto-Bismol, or take Tums, or Rolaids, or baking soda and water, you can drink that. If you're like upset stomach, what you're doing is this. You're not drinking this. That'll mess you up. All right, but if you have acid in your stomach, when you add something like a base, again, Tums, Rolaids, Mylanta, whatever, Pepto-Bismol, whatever makes sense to you, you understand. If you drink it or take some of that stuff, this is what you're doing. You're creating water in your stomach. You're neutralizing acid. So sometimes when you have indigestion, heartburn, or upset stomach, your body, for some reason, at that point, is producing too much acid. So when you drink antacid or baking soda and water, you can actually just stir it up and drink it, and it'll help you feel better. This is what you're doing. You're neutralizing the excess and creating water in your stomach. So that's what's happening when you eat food, when you eat antacids. A lot of foods, though, tend to be acidic. So, but the concept here is really important. Acid plus base, you always get water, and then you always get some sort of salt. This happens to be what we call in salt. What? This happens to be what we call in real life, which is salt. But another example, this is called a salt. It's calcium chloride. It's not actually salt. We call NaCl salt. In chemistry, the term a salt, I know this is weird, I've said it before, this just means an ionic solid. Metal, non-metal, we learned that already, hopefully. Alright, so you always get water and some sort of salt, because when it's a double replacement, the H and the Na switch. They switch with each other. So now Na is bonded to Cl and H is with OH, and that's what I'm trying to show you here. If you substitute in another element, so another base, like KOH, you would get KCl. That's called a salt. I'll give you another example in a minute. But this is what titrations are. So a titration, here's a base. Now, if I put phenolphthalein in a base, what happens? Look at table M now. Phenolphthalein in a base, this has a pH of, we'll say 12.
It'll turn pink.
Pink. So observe. You've seen this before. Oh wait, this is the acid. I'm sorry. How do I know that?
It turned colorless.
Because it's colorless. So I forgot what I put in here. Hey, that worked out. So that's why indicators are useful. I forgot what I put in here, but now I know I put in the H. So in here I have HCl. How do I know? Because it's less than 8, it stayed colorless according to table M. So what I want to do is neutralize the acid by adding sodium hydroxide. So when I add sodium hydroxide to this thing, it'll turn pink temporarily. But it goes away. Why is it going away?
Magic. Because it's still under the pH rate 8.
So what's happening here is originally in the beaker, it's only, not only, but the majority of the ions are H+. Well, when I add, I just did it. I just poured the base into it. I'm adding all these OHs. What are they doing? They're making water. So as long as that stays colorless, the base, the OHs are completely gone. They're completely being reacted with H+, meaning it's still acidic because of this neutralization. So every time you see the pink disappear, it's because the H+ is neutralizing those ions. The only time it stays pink is when you have a lot of these. So if I keep adding the base, eventually these will overpower the H+, and it'll stay pink, hopefully. The beaker's getting pretty full here. There you go. Okay? So now it's going to stay pink because I have more OH minuses than H pluses. So essentially what I did was, I gotta go wash my hands. Hold on. You don't want base on your phone. It's not good.
If it always creates water, can you drink it?
Yeah,
Yes.
I was gonna ask.
Are you going to?
No.
Not.
So, you can always tell when you have base on your thumb because it's slippery. Bases are slippery. You guys actually know this. What did Miss Carr come in and show us?
Water. Soap. I don't know. do not know why I just said water.
It's okay. You hear me say crazy things up here. So yeah, she Susie sells seashells by the seashore.
Sally.
Yeah.
Sally, I'm sorry. Susie did sound too easy. Anyway, Mrs. Carr came in. Mrs. Carr came in and made soap. What are the two ingredients? You need fat, which you use
Lye.
oil. The lye was this. Okay, it's a concentrated sodium hydroxide. So the soap is slippery. If you've ever held soap in your life, of course you have. It's slippery. That's because bases are slippery. That's the property. Anyways, back to this. Now, this did create water. At one point, when it was extremely light pink, and that's what I'm going to show you in lab. Mr. Decker will show you. When this is extremely, very, very, very light pink, almost kind of like this worksheet here. This color is essentially pretty close to a 7. Now, it's confusing because on table M, according to the range, 8 to 9 is when it changes, right? So 9 and higher, it's pink. 8 and lower, it's going to be colorless. But the rule in chem labs, it's not just my rule, it's all chemistry classes, is when you're doing this titration neutralization stuff, you're adding acids and bases, when this is an extremely light pink color, like very light, and again, you'll see it in lab next week, that's considered a pH of 7, and you could drink it. Because when that's a pH of 7, all we have is salt water. So technically you could drink it. No, I'm not going to. No one's going to drink it. Alright, because it's dangerous, because what if it isn't a pH of 7? Plus you don't drink or eat anything from back there. But that's the theory here. That when these are mixed perfectly in a pH of 7, which this is not. I went way past the pH of 7, now I'm above 9. Then you would only have salt water. So I'm trying to kind of teach a couple things at once here. What is the titration? I kind of just showed it to you. This setup over here is how we actually do it. And what is neutralization? I just showed it to you. It's one and the same. It's when you mix acids and bases to get water and some sort of salt. All right. So let me give you another example. Let me show you the setup, and then I'll show you how to use that titration equation. All right. So let me show you the setup first. All right. So this contraption here is how we do it, and I'll have to hold it So in here, what is this thing called?
Is that a pipette?
Starts with a B.
A bee?
It's a burette. It's a
That
burette.
was close.
So in your notes, what I want you to do is just sketch this setup, like very quickly. Don't get all artistic on it. Okay. So draw like I'm gonna, which is off. So just draw a burette with an Erlenmeyer flask under it. You don't even have to draw the stand. Just draw a burette with a flask underneath it. This is the setup that you're gonna use in lab. I'm gonna put it on the board so I can label it and explain a little more. But I'm just showing you guys this because this is actually in the setup. The burette will hold the base. That's always easy to remember. Burette base, we'll start with a B. So you would fill this thing up with NaOH. Down here in the flask would be HCl. And you would use phenolphthalein, just like I showed you. And there'd be a pink, colorless thing going on here. So you would add the base from the burette into the acid. When this turns light pink, the titration is over and you have a pH of 7. I know I'm kind of saying a lot. I feel like I am, and I'm going over a lot. But it's good because you need to hear all of it, and then when you practice it, it's going to make more sense. So in a titration setup, essentially what you're doing is a neutralization. In the burette, all right, here's our burette. You're going to have the meniscus. Remember, I always read that meniscus. This is going to be like 1 molar NaOH, meaning the molarity of the base is 1. You're going to have a flask underneath the burette. So in here, all right, in here, now here's, I just squeezed it a little hard on one side. So now in here is our HCl, but here's the whole purpose of a titration, and you're going to do this in lab. Mr. Decker and myself, we're going to give you guys 3 unknown acid solutions. We'll tell you what it is, but we're not going to tell you the molarity. So what you're going to do is you're going to put a couple drops of phenolphthalein in here. It's going to be colorless. You're going to open up the valve. You're going to let base kind of drip into this. You're going to have base flowing into here. You're going to keep track of the volume of the base. And when this thing turns light pink, you turn the valve off, and you can use that formula to calculate this molarity. That's the explanation. I know you're not going to learn it just from the explanation. I'm not even really showing much, but that's the gist of it. So your volume of base, maybe it starts at 0, you add a bunch of base, this thing turns light pink, and let's say your final volume here, so all of this you added, let's say it was 20 milliliters. So you know you added 20 milliliters of 1 molar base, 1 molar NaOH, and now this is neutral, pH is 7. Now you use this equation, MAVA equals MBVB, to solve for that. That's what you're going to do in lab. And again, I realize right now in class, you're like kind of like, what's going on? I get it. You're going to apply it to lab, and it's going to make way more sense when you do the lab. Today, the goal is to be able to use this calculation, use this equation to do calculations, and I'm going to do one with you right now, and then give you the worksheet. But this is what titration means. You're given a known base concentration. You don't know the acid concentration. So teachers, students work together. You figure these 3 out, and then this is your X. So it's really just these 2 multiplied, divided by that. It gives you Mn. And I realize I'm going fast and kind of vague. I'm going to do an example with you. But the goal today was kind of show you another example of neutralization. Same thing you've seen multiple times. What is neutralization? Acid plus base makes some sort of salt and water. And then what is the titration? This is the titration. Again, in lab, you will really understand it because you'll see it. So, 2 things I want to do right now, and then I'll give you the worksheet. I'm going to give you one more titration example, and I'll use that to teach how to do this equation here, and then you can start working on that. Questions before I move on? I'm smiling because Sean's face is priceless. Sean's like, just get on with it. All right, here we go. H2SO4 plus, let's see, KOH. All right, this is another example of a neutralization reaction. How are you supposed to know that? There's only one reaction between acids and bases, and that's called neutralization. That's it. There isn't a whole bunch of like organic, there's a whole bunch of reactions. Acid and base, this is it. This is an acid, this is a base. How do I know that? How would you know that?
Because KOH is on the
Good. KOH is on table L, and
H2SO4 is on the table.
is on table K. That's an Arrhenius acid, that's an Arrhenius base. They're both Bronsted-Lowry acids and bases. So that's your first clue. That's an acid, that's a base. What does that mean? Oh, neutralization. What are the products?
Is it a HOH?
You always get HOH. You always get water. HOH again, which is H2O. Same thing.
KSO4.
Good. K is now bonded to SO4, but of course, it's not that easy. I gave you a tricky one. It's not just KSO4. No, those are everything's right. It's KSO4 and HOH, but we're missing a substrate.
Because we're missing an H somewhere.
No.
Don't worry about the H yet. We're going to balance this when we're done. KSO4 is not correct. There's a subscript somewhere. You guys remember how to form compounds? Like, why is CaCl2? Now, why?
K2.
Yes, very good. It's K2. So, I'm not going to completely reteach it, but real quick, K is +1, SO4 on table E is -2. I need 2 of those to balance that out, so it's K2SO4. Okay, moving on. Now, balance it. It's not balanced. You want 2 of these?
Yep.
I like that. Very good. Good job, Sean. That's the other reason I write HOH. H2O is confusing because H2O has an OH in it. So here, look up here. Stay with me so you see what I'm explaining. This has an OH, but you can't see it. When you write HOH, you can see it. Now you can balance your OHs. So I have 2 H's, 2 H's, 2 OH's, 2 OH's. It's just easier to balance when you write HOH. All right. So this is a neutralization reaction. Acid plus base, salt and water. This is called a salt, potassium sulfate, and there's your water. So that would be a pH of 7. Here's my titration question that'll help us practice this equation. MA/BA equals MB/B. Here we go. So write this question down. In a burette, 1 molar KOH is added to, so in a burette, you have 1 molar KOH, that's the base, in a burette, is added to 20.0 milliliters of H2SO4. So that would be the flask on the bottom. So you got your burette with the base, the flask underneath it is the acid. This is your acid. If, do I want to make it easier or hard? If 10 milliliters of KOH, if 10 milliliters of KOH is needed to neutralize all the H2SO4, calculate the molarity of H2SO4. I know it's wordy, but that's how these problems are. So I'm just going to draw a little picture here to help us kind of visualize it here, and I'll draw my cool flask again. That's better, a little bit. All right, so here's my H2SO4. Up here is my KOH. So we're dripping the KOH into the sulfuric acid. We probably use an indicator, not probably, you have to. You have to use an indicator or else it'll never change color and you'll never know when this happens. The indicator, that pink, that light pink, again, you'll see it in lab, that tells you to stop adding base. So the indicator turns color once we've added 10 milliliters. So we added 10 milliliters of the KOH. we added it to 20 milliliters of the H2SO4. So I gave you 3 numbers out of the 4. You are solving for MA. I gave you VA, I gave you MB, the molarity of the base, the volume of the acid, and I gave you the volume of the base that was added. So without me going over it, let's see if you guys can come up with the answer. I gave you all 3 of these. What is the molarity of the H2SO4? What is the molarity of the acid? And if you can't do it, that's fine. We're going to go over it in a minute, a couple minutes. So give it a shot on your own. This is a typical question for using this equation. And typically on a Regents, they would say show both the numerical setup and calculated result. And typically they might ask for significant figures. Now the problem is I left that at 1. I probably should make that 1.0. So don't worry about that too much right now. I'll explain it when I go over it, but I probably should have said 1.0. Bless you. Okay. Does anybody have an answer they'd like to share? What'd you get?
I got 0.5.
0.5? Okay, let's find out. So MA is my X. What is the volume of acid? What did the question tell us? How many? 20, right here. 20 of H, that's the acid. So 20 goes here, 20.0. That's VA. MA, I don't know. That's the molarity of the acid. What is the molarity of the base? Up here, I told you, 1. 1.0 if I did it correctly. What's the volume of the base that we added? 10. Again, in lab, you're going to see the color change. Once the color changes, you stop adding base, and that's where you get that number from in real life. The lab really will help with this. So that's 10. How do we solve for x? 1 times 10 is 10, equals x times 20, divide by 20, divide by 20. I'm going quick because the math is easy. You just need to plug in the right numbers. 10 divided by 20, x equals 0.5. And if it was sig figs, 3, 2, and 3, we go for 2. So 0.05, capital M, would be the answer. You always have to label molarity, capital M or moles per liter. So, we got a little time. I'm going to give you the worksheet. You can start on the first problem maybe. I did everything I wanted to. I went kind of fast. But that's neutralization and that's titration. So this worksheet will be due on Monday. And there is a little bit of a back too. So I know it's the weekend, but it is what it is. We're almost done. We have one more unit left, which is good. We're getting closer. All right. So if here, don't put it away. You got 4 minutes. Let's try and get number 1 done. So number 1 is exactly what I just showed you, except it's a little bit short, right? It says calculate the molarity of 50 milliliters of NaOH that has been neutralized by 25 milliliters of a 0.2 molar solution of HCl. So in this one, I give you the molarity of HCl, that's the acid, and I'm asking for the molarity of the NaOH, that's the base. So again, you're using MAVA equals MBVB for this whole worksheet. But in number 1, you're looking for MB, not MA. So the example I gave you is similar, but not exactly the same. The key to doing these problems is identify who's the acid, who's the base,
Does it not matter what side it's on?
as long as the numbers are together. Right. Yep. So Selim said, does it matter? So if you put MB and VB on the left and MA, VA on the right, that doesn't matter. As long as the two base numbers are together and the two acid numbers are together, that's fine. Doesn't matter. Because it's proportional. That's what that is all about.